By the end of this video, we will understand why the gambler's ruin equation is what it is. Let's get started. You are given the following information about when a fair coin is flipped. If the outcome is heads, one chip is won. If the outcome is tails, one chip is lost. The gambler starts with 20 chips and will stop playing when he either has lost all of his chips or he reaches 50 chips. Of the first 10 flips, 7 are heads and 3 are tails. Calculate the probability that the gambler will lose all of his chips given the result of the first 10 flips. First off in this problem, we need to understand that it is a gambler's ruin problem. And the way that we know that that's the case is that it's a set of conditions where you have some number of tokens or dollars or points, and there's only 2 stopping conditions. You're either going to stop when you reach a winning amount or stop when you reach a losing amount. And that's very much set here. So we know that we're going to be using gambler's ruin equation. For required knowledge for this problem, all you need to know in terms of if you want to do bare minimum memorizing of formulas is just that when you're dealing with gambler's ruin and it's a fair game that is 50-50, the probability of ruin is 1 minus the starting amount dividing by the stopping amount. So pretty straightforward there. Feel free to skip the next 10 minutes of talking, but what we're going to do now is revisit. This is actually the same topic covered in an older video, which is the derivation of this equation. So let's just go ahead and jump into it. So first off, we're going to not assume it's a fair game. So instead of assuming 50-50 win-lose, we're going to actually denote it L as the probability of losing a round, and W the probability of winning a round. We're then also going to say that P subscript I is the probability of winning it all. So in this specific problem, we win once we have 50 chips. So this just means given I have I chips, what's the probability I'll eventually get 50 chips? So L and W correspond to rounds, P corresponds to the overall series. And all this is saying is, let's say we're playing to 50 chips and we have 25. Well, the probability of winning with 25 chips is the same as the probability of losing 1 round multiplied by the probability of winning with 49 chips, or 24 chips, and the probability of winning multiplied by the probability of winning everything given I start with 26. So all we're doing is saying, hey, whatever, that first coin flip, there's 2 possible outcomes, and what are their corresponding probabilities, and taking them both into consideration is the overall probability. So you can either win or you can lose, and then, that probability multiplied by the remaining probability of overall success, given those conditions. And that's that subscript I minus 1 and I plus 1. Also, we're playing a game where you either win or lose a given round, so L plus W equals 1. So what we can do is multiply the right side of this first equation by 1, and it's written out as L plus W. And then, let me see here, we get like terms together, so we have W plus PI plus 1, and then we subtract the PI times W from the right side to get it over here. And then likewise, we have P subscript I times L, and then we subtract L times P subscript I minus 1. So we have this, and then finally we divide both sides by W. At this point, I'll pause for a second to say this is very much one of those derivations where I did some research, and people far smarter than myself determined all this, and I have no idea how someone gets to the point where they want to get to the bottom of this and they know to end up going through this process. So this is very much one of those, I see each individual step and understand it mathematically, but by no means did I just kind of sit down and work all this out on my own. So just want to give credit where credit is due. I'll have links in the description of the video of the resources I use to get at this. That being said, at this point, this is a key formula to have. So we know the probability of winning the overall system given I plus 1 starting tokens, subtract the probability of winning with 1 fewer tokens, is equal to this ratio times a difference of I starting tokens and I minus 1 starting tokens. And so what we can do is use the special case of I equals 1. So the reason why this is special is because when you use I equals 1, this I minus 1 is just 0. And so what is the probability that you will win the overall game given you start with 0 tokens? Well, by definition, you've lost once you get to 0 tokens, so the probability of winning is 0. And so we end up with this simplified result. Now what we can do is just move 1 up, so now we'll consider I equals 2. We get something similar, and what we can then do is say, hey, this looks familiar, this 2 minus 1. I actually have seen that before in this equation. So when we plugged in I equals 1, we know that this left side equals L over W times P1. And so we can actually just sub that in to this result here. So we're subbing in for this L over W times P1. And what we end up getting is P3 minus P2 is the exact same quantity, just multiplied by an additional L over W. So it's the same thing, but now it's squared instead of to the first power. And again, you can just then take this previous result, plug it in, same thing happens, and we just get an additional L over W factor. So this is not a formal proof by induction, but at this point I'm just saying you can pretty clearly see as you increment up by I, you're just multiplying by an additional L over W factor. So we get this formulation here. Now what we can do is say, okay, well, what if I sum up all of these differences, starting at I equals 1 all the way up to K? Well, that's going to be equal to the final positive, subtract the the first positive upper limit, and then subtract the final lower limit. So the reason why is when I plug in K plus 1 minus K, but then the very next sequence is going to be K minus 1 plus 1 is just K, and those terms are going to cancel. So all the terms in between cancel, so all we're left with is this P subscript K plus 1 subtract P subscript 1. We then can say, well, okay, I have a specific formulation for this, right? It's just L over W to the power of I times P subscript 1. So I know that we just solved for this here, but I can also say that it equals this summation. So L over W to the I times P subscript 1, and just summation of that from 1 to K. I then, to simplify and use some formulas for summations, I'm going to add to both sides just P subscript 1. So that's going to cancel this on the left, and the reason I'm doing this is because then on the right, this is going to be the same as being able to then just start my summation at I equals 0, because the L over W is just going to become a factor of 1. So really this is being done so that way this we can end up using this formula we have down here for summations. So we now have P subscript K plus 1 equals P subscript 1 times the summation, where the factor, and I had to look this up, I know we learned this in high school, I had forgotten it, but just copying in L over W for our factor A, we end up getting this result. So that's just plugging and chugging, and then just to simplify the notation, all references of K are K plus 1, and that's just arbitrary. K could be anything, so just chose to write it as K. Or we could have, to be more formal, changed the letter so it's not the same. but that's just simplifying because there's no k by itself, so this is unnecessary to have this k plus 1. Okay, so at this point we have p subscript k equals some function of p subscript 1, L, W, and k. So that's good. So now what we can do, because what we'd really like is to, we don't know what p subscript 1 is. So in an attempt to solve for that, we can use another special case. So before we use p subscript 0, we know has a probability of 0. Well, we also know that p subscript n means you achieve the goal, and so the probability of winning the overall game is 100%. So we can plug that in, say it's 1, and then for k, plug in the value n. And we get this, and it simplifies to what we have here below. Divide both sides by p subscript 1, and then put both sides to the power of -1, so it's just the numerator and denominator flipping. So we now know what p subscript 1 equals, just in terms of LW and the known stopping condition. So we go back to our previous formula we had for the generic k case. We also have learned what p subscript 1 is, and so we just plug that in. So we get this mess on the right. And then we see that the numerator on the left and the denominator on the right are the same and they cancel. And so we just end up with this formula. The one final step is, I don't know why this is the case, but the notation used is ruin, so the probability of loss. We've been solving for the probability of success. So to get that, it's just going to be 1 minus the probability of success. So that's why the terminology is ruin, so we're going to do 1 minus everything we just solved for. So at this point, this is not needed for our specific question that we're going to be solving, but this is the formula that you should have memorized for MAS1. It's come up, I think, on 2 of the past published exams. You might get lucky, as in the fall 2018 exam where they use the fair coin flip case. But this is a simple enough formula and has come up enough times. I think this is definitely worth taking the time to memorize. So again, this is, you're playing some game or flipping some coin that might not be fair. L is the probability that you lose the bet. W is the probability you win the bet. K is the starting amount of points or dollars you have. And N is the stopping condition. And also built into this, 0 is assumed to be the stopping loss condition. So if, the rules of the game where if you get down to 10, you're going to quit, then you need to subtract everything by 10. So that way that lowest value, that stopping condition is 0. So that's the generic case. Definitely have that memorized. But we know that it's not this formula that we had above. It was 1 minus starting divided by stopping condition. And the reason why is you can't plug in 0.5, right? If we have a fair coin, L over W is going to be 0.5 over 0.5, which is just 1. To the power of k, it doesn't matter what k is, and then we have 1 minus 1. And same thing in the denominator, and we're going to be dividing by 0, which, that's a no-no. So again, going back to some high school mathematics I had forgotten, you need to end up applying L'Hopital's rule. So all that is going to end up doing is we're going to take some derivatives and see what the limit goes to. So again, I haven't touched on this since forever, but suffice it to say, when you take that limit, you determine that when the coin is fair, you just end up with k over n is the probability of winning. So the probability of ruin in the unfair case is just going to be 1 minus k over n. And that's what we have here. So with all that said, again, that's probably more information than you wanted, but I put the work in to understand it initially, so I figured I'd share it. The calculation's super straightforward. So I'm actually going to scroll up to the problem because I think that's more useful to look at. So here we have, we start with 20, and we're going to stop when we get to 50. However, 10 flips have already occurred. So we know that 7 were heads, and I win when it's heads. So I don't have 20, I have 27. But then there are 3 tails, so I lose 3 bets. So 27 minus 3, I have 24 coins. And I'm going to play until there's 50. So 1 minus 24 over 50 is just going to be 52%. Is the probability that I will achieve ruin or lose the entire game. And that falls in the range of B. So B is our final answer. Thanks for watching. If you found this video helpful, please consider liking, commenting below, or subscribing. Have a good one.